high frequency. Your sampling frequency is high, alright? Therefore, listening for the echo signal is known as pulse time. And after you have sent one pulse, you listen, and then whether there is a signal or not, you analyze it, you do a mass filtering and so on, and then you send another pulse. So this corresponds to each pulse. Follow? And this is of course the pulse repetitive frequency is lower than your sampling frequency, and therefore you have the so-called slow time axis. Alright? Okay, so here when you see a picture like this, from 0 up to L minus 1, that would mean you have L bins, L range bins across horizontally from 0 to N minus 1, so you have N thousands, so you have in this case N thousands. And for each range bin, well, you basically have a set of time samples. You perform FFT, and that will give you the so-called frequency spectrum for each range bin. Alright? So here, well, you notice that they are in gray, so that means there is no target signal being received. But for this particular row, you have a set of squares colored in green. That means there is actually a target around. But the question here is, at what speed the target is moving? So what you do is, well, for every row, you perform FFT. If there is a signal when you perform FFT, and the FFT turns out to give you a certain spike in the frequency spectrum, you know that Doppler frequency corresponds to what? The speed of the target corresponds to its Doppler frequency. Alright? So if you see a certain spike in a certain frequency bin, so this is your frequency axis, well, you know that there is a target corresponds to a certain frequency, so you can reduce the speed of that target. And you can single out there is a target moving at a certain speed. Right? So that is your basic idea of your Doppler pulse processing. Now, in some situations, you find that using the Doppler approach will not give you good target detection. So if your radar is a ground radar and you have a target flying in the space, so you emit pulse, signal received, well, you see that this is static, or you don't see, seeing being reflected by objects or terrain in the space. So therefore, the Doppler process will allow you to detect the target and in fact to single out the target. Alright, but what happens if you have this scenario? So you have a flying object and you are up here. So you have your antenna array here, right? And on the ground, well, you have mountain, you have sea, you have lake, right? You have buildings. So if you to emit a signal, what happens? You get a return echo from your target. You also get return echo from the ground or from the terrain, right? So this is known as what? Clutter. Okay, so you get the return echo from the target. You also get the return echo from the background, and that is known as clutter. Now, you are an airborne radar, so you are actually also flying, right? So this clutter will also give rise to Doppler frequency to your received signal in your airborne radar, and likewise for this case. So the question here is how to separate them. Now, in signal processing, to separate signals, usually you do it with this few possible approach. When the signal is, appearing at different instant of time, you basically put a range gate or time gate. You can separate them. So this is time. If you have signal appearing in frequency domain, different sinusoids, you put a bandpass filter, you can isolate this signal from that signal. Follow? So this is separating signal in frequency domain. Now,